Hey folks, we're just going to give it a couple minutes because people are still on their way back from lunch.
Good morning, this is Ingmar Johansson here. Do you hear me?
Hi Ingemar, yes we can hear you.
Yeah, I'm great. And at least that will work. So, and I'm using my microphone meanwhile.
Sure. Just discussion is fine. Just discussions, yeah, thank you. Just because of the video. I think they're trickling in now. But I think we can just start in a minute or two maybe. Because people are coming in right now. That's true. That's true. Actually, you could just press next on your laptop. Huh? Yeah, yeah. No, I mean, I could also do it myself. Oh, you could. That's what I was saying.
Snake Game, I think, is the killer app right now. Yeah.
It's great.
Ever since flip phones went away. That's why they named it Flipper.
Okay, we're starting at 5 past, so that's 2 minutes.
Thursday is the congestion control day. You can spend your whole day just thinking congestion control. In case you didn't think your brain heard. Yes, roughly 60 seconds to elapse.
Okay.
Indeed.
Indeed, it is. Yeah, there we go. Okay. Hello, welcome to the Congestion Control Working Group. My name is Reese Enkhart and I'm co-chairing with Eric Kinnear. This is a hybrid meeting and also being recorded. Just a reminder to use the buttons in the media code. Chances are you have a bit of experience with them already. This is the Note well. You might have seen a few of these by now. It's the terms under which the IETF operates, please make sure you actually do read it at some point. We also have a code of conduct, and it's because we're here to make this working group a success, right? And part of that is making sure that our working group is a friendly and inclusive space that people actually like to participate in and they feel, invited to. So let's make sure we're being professional and respectful to each other. And if and when something comes up, please reach out to us as chairs. You can find us here in person. If you're here in person, you can email us. We can talk via email, video chat. You can also reach out to our ADs or the ombuds team. So here's a couple of helpful links, mostly for people who are reading those slides who are not in this meeting already. And right, and here's our agenda for today. So we already have a scribe. Thank you, Mathis. And we have a couple of agenda items. Is there any agenda bashing by any chance? Okay, so if not, we're going to briefly talk about 5033 bis, which has matured quite a bit. And then we're going to spend some time talking about other items. And at the end, we're talking next steps for CCWG. So I'm very excited. And I would like to invite Martin up first.
Thank you. Good afternoon, everyone. I'm Martin Duke. I'm one of the editors of 5033 BIS, along with Corey Fairhurst. This just concluded working group last call about a month ago. That we got a few issues, which are mostly resolved. I think there's still one open PR, but it's not, frankly, a big deal, I think, to resolve it. We didn't get a ton of reviews. Given this is the only deliverable for the group right now, is a little disappointing. So as punishment, I'm not going to read the draft verbatim to you. I'm just kidding. I am, however, going to kind of run through kind of the. I would hope that maybe a few of you would read it in the next few weeks before we move things forward. And so I wanted to give a little kind of high level. Here's what you should expect. Here's what you should be looking for. Kind of points. Next slide. Oh wait, no, I have a thingy. Never mind. Okay, so many of you know this already, but the main purpose of this, so the 5033 is a series of criteria to evaluate congestion controls for standardization. It was written in I think 2005. It was a very different internet in a bunch of ways. In particular, certainly in congestion control space, usually proposals would come from the academic community. Just because the resources available to academics in general, you would have maybe some simulations, maybe a very small scale deployment on a campus network or something. That is not the situation we face today. We have hyperscalers proposing new congestion controls, deploying them globally and getting like enormous amounts of data about them. The kind of flip side of that is those people don't feel like they need to come to the IETF for any sort of standardization approval before they deploy, which maybe shows that in some ways the system is broken. We had a very recent experience standardizing Cubic, which was not. I see at least one of the co-authors here. He did not enjoy that experience. He would give it very few stars, which is in some ways absurd because obviously Cubic is the default in Linux in the internet among other platforms. So anyway, so that sort of informed all this. So hopefully, not only can we make that less painful, but also the other sentiment that was kind of driving this is that we think the current standards, Cubic and Reno, are the only current standards, have some bad habits in them, particularly related to buffer bloat. And by being sort of conservative about our interaction with those standards, we're perpetuating those bad habits. So maybe we can come up with something better. This document also has a lot of non-goals, and one of the tasks of us as editors was to kind of beat away PRs and other suggestions that were kind of good and correct in their way, but also maybe orthogonal to the purpose of the draft. So this is not a congestion control tutorial. We will try to limit the extent to which we are teaching people how congestion control works. I expressly did not want to be cutting edge or innovative here. We got some really good ideas for like new metrics on how to think about congestion control. Very clever, very interesting, but maybe a little too bleeding edge for what we're trying to do here, which is encapsulate our current understanding of the space. This is also not to create barriers to entering the IETF. We, after reading it through a few times, we realized that someone could look at this document and say, oh, well, this is a checklist of things questions I need to answer before I come here. And that is actually that's not what we want to do. And so I added that paragraph in the intro there, gosh, probably 6 months ago, with a part bolded there, just like, no, you don't have to check all these boxes when you get here. Just please be prepared to engage with us on these topics as we go. Also, multicast is not a topic. AQM is not a topic, except to the extent that they directly interface with a congestion control. Okay, so let me just run through some of the highlights of the various sections. Section 2 just talks about experimental versus PS and just has some principles that should be applied here. Tries to say, well, what does it mean that an RFC is experimental versus PS? What do we want to, what kind of congestion control is maybe best done as an experimental one first? Which ones might be comfortable to go straight to PS post standard? Okay, so there's a few sets of criteria. This is really complete reorganization, 5033 bis. I found the way that those points were laid out to be a little bit confusing and not particularly well categorized. So we took another shot at it. So our first set is just single algorithm criteria. So these are taking a congestion control proposal and how does it interact with itself in a number of different with different metrics, with different sort of models of flow lengths. Then we have mixed algorithm criteria, which you would expect. The internet, of course, has a number of congestion controls that are widely deployed, and we should definitely look at how the new proposal interacts with those. There's some very vague language about real-time congestion controls. I think last several IETFs, we had extended discussions on what can we say here, given that what is deployed is often not documented and what is documented is not deployed, at least in RFCs. I do want to call out here that we are not, the one, I think, real intentional softening of the language was on this idea of Reno and cubic fairness. That was like a very conscious decision. We definitely cannot starve those algorithms, but we want to have a little space to maybe nudge them out of the internet as we go. Zahid, you had a question or comment?
Jahid as individual. So the real-time congestion controller, ARMCAT, has published some requirement documents. While have we looked into that one, and can we generalize something from there? Because I know what is documented in ARMCAT is not deployed, and what is deployed is not correctly documented somewhere. Yes. But the requirements remain same.
I'm 95% sure that we name check the RMCAT documents in the draft. Okay. So it's not like we're ignoring them, but because our statement is oriented around let's make sure we test against the things that are widely deployed, it was kind of hard to say I'm of the position that I'm not 100% sure that we need to. That I'm not sure what guidelines to place about how fair or non-starvation we need to be with respect to the RMCAT algorithms, given the level of deployment right now. Now that environment that could change as if they gain wide adoption and people start deploying those algorithms, then it would become more important. But to me that's a difficult normative statement to make right now.
Yeah,
that's my personal opinion.
Yeah. Okay.
Next, whoever's next in the queue, Christian.
You want to take queue now? Okay, Christian, please.
Yeah, I mean, I just want to reinforce the point that you're making about general purpose congestion control, comparison, etc., being fair. One of the big aha we had when working on this document is that being fair has multiple dimensions. We used to measure being fair by looking at, okay, we do a simulation, we pit algorithm A against algorithm B, and we verify that they all have the same share of the bandwidth. That's one dimension of being fair. There are other dimensions of being fair, like if you pit algorithm A against algorithm B, do you suddenly increase the packet loss rate for algorithm B, even if you do have equity of bandwidth? And that would be bad. So you don't want to do that. Or do you suddenly increase the round trip time experienced by algorithm B? That would be bad too. So I think one of the value of what we're doing there is say, hey, be careful when you analyze, because there are several dimensions, and it's okay to be a bit fuzzy on the bandwidth equality if in return you get lower latency or lower packet losses, for example. I mean, this idea that there are multiple criteria and there is no strict thing, but you have to control what you are doing and you have to understand what you're doing. That's the real point, in my opinion.
Thanks, Christian. Lars?
Lars, to follow up, I came up to say something else I'm going to say later, but to follow up the question, maybe something that we could put in a document would be that, if you're running against, is this even on? I guess it is. I just have to go real
kiss the mic.
Maybe we put something in a document that would say something that you shouldn't impair the path so that other protocols are outside of the operating region. Or I'm making this up as I go, but you know what I mean.
Yeah.
So basically, not just talking about
Yeah.
throughput, but sort of creating a path environment where others are.
Yeah, we spent a lot of time wordsmithing that. Christian
Right.
made significant contributions to it. I really invite people to just read what is there and comment on it, because it is a pretty delicate way, pretty delicate thing to express.
Yeah, the thing I came up to talk about is the real-time CC stuff, which is sort of different. No, in the sense that, I mean, typically real-time workflows have sort of an upper bandwidth cap, so they're not like bulk transfers. They will just use like however much they want, right? So that is nice, right? So the harm potential here is lower because they will only like interfere up until they get their happy place, and then hopefully gonna stop ramping up. The other thing that's different is that they're typically deployed in interactive conferencing systems, which have pretty tight feedback loops about how the quality is, because the deployers of those systems want to, not make their users unhappy. And those feedback loops are probably much more real time than the ones we see for like traditional TCP and other congestion controls for bulk transfers. I mean, hyperscalers have that too, but it's a very different kind of control loop length than in a video conferencing system, where basically you get frame by frame almost information about how am I presenting this to the user. So those two things together, I think, don't make real-time CC as problematic as we thought it might be when we did our MCAT, which like with the rise of WebRTC, right? We were wondering like, what the hell is this going to do to the network? And I think in hindsight, right, the problem is probably more controllable and more controlled and not as bad as we thought. And so it's okay maybe to not lump those in here.
Yeah. So thank you, Lars. So I think some of the sentiments you expressed on how the dynamics, the properties of real-time congestion control are in the document very concisely. But to go back to my initial point, we're not trying to write a tutorial and trying to focus on what do you actually have to do, what do you have to show, and so the language on what you have to show in this regard is pretty soft for some of the reasons that you describe, and also for the practical reason that there's just it's hard to define a good test when no one's written down what the important protocols are doing in a stable way. Okay, so I talked a little about criteria. Now then, there's also scenarios. There's a set of mandatory scenarios, which are kind of the general internet, I would say loosely. And so, I mean, these are kind of the canonical cases. And so you really got to have, you really got to look at this before you standardize something. Preferably you have real data about, if you deploy over the general internet, you will generally also get results that are relevant to these particular scenarios. Then we have special cases, non-tail drop AQMs, and all these other things you can read. These are things that are kind of rare enough that you might not get good data just by having a general internet deployment and just sort of aggregating everything together. So you probably have to look at them separately. You could do them with simulations with analysis. You should be prepared to talk about these. It is possible in many cases to exclude a particular scenario from your applicability statement at the beginning of the document, depending. So this is a little looser, a lot of shoulds here instead of musts, but this is just another segment of the document. So yeah, as I said earlier, working last call is complete. It is not too late for reviews. Please have a look. When the chairs decide they've had enough, then we'll move it forward to the AD. If there's something that seeing this outline, you think, boy, you really missed the boat and you need to either change or add something, this would be a good time to bring it up. And if anyone thinks that this document is ready or not ready, this would be the time to say so. And that's it.
Thank you, Martin, and Corey. Hello, microphone. Yeah, we've seen some really good engagement from a number of folks with great feedback coming back. But that number of folks has not been a super large number of folks. So the feedback that we've been getting has been really in depth and is greatly appreciated. But this is very much a good time to, if you have not recently read through the latest version, perhaps during the last call, this would be a very good time to do so. I see Corey just joined the queue.
Yeah, everything Martin said, I agree with. So the reason for joining the queue was Jonathan Lennox said in the chat, should data center really small RTTs be included among the special cases, Martin? Working group, what do you think?
Yes, I guess I haven't looked at it. I'm a little surprised I forgot it because certainly data center was in scope for the working group when we wrote the charter. So yeah, that's a good point. Can you add an issue, Gory, while you're in front of a computer?
Filing one right now.
Yeah.
Oh, excellent. Thank you.
And I guess it is important to add something on this topic because when the original spec was produced, the data center work was explicitly out of scope of what the IETF would actually standardize. It was thought as being a different area and wasn't really the internet. And I think that has changed in our thinking over the years. So yeah, it seems a good comment. I think we should do something. We'll make an issue.
Yes. Yeah, that should be straightforward.
And if we make an issue, we need people to comment on the issue in GitHub as well, because Martin and I are trying not to make this up ourselves. We need people to have opinions and to help us make the right text.
It strikes me as a straightforward section to add. So yeah, we can try to put something together. But if you have a PR to offer, we will definitely accept it or look at it. Christian.
Yeah, regarding the data center, the problem is that we have to be very specific about what we mean by data center. There are some data center scenarios that are uniquely data centers, like for example, sending a Hadoop query to 1,000 nodes and have 1,000 nodes coming back at the same time with results and trying to organize that. I mean, these kind of scenarios are not typically found on the internet. So, if we do something with data centers, please, Jonathan and others who want to look at that, please give some details about the scenarios, the data center scenarios that you want to take into account.
Lars, yeah, Christian has a good point. The other thing that's sort of special in data centers is that typically you see these co-designed forwarding plane congestion control proposals, right, that are really relying on the fabric doing something non-internet-y. And those are interesting, right? But you got to sort of describe both of them together, and that's the thing that doesn't make them usually applicable to the internet. But they're still interesting, and we should still, like, people can present them, but they should tell us what the data plane is doing too.
Thanks, Lars.
Thank
and as
you.
your incentive to, I know a lot of people in this room are actually here to standardize congestion controls rather than argue about process. Your incentive for reading this document is then we are completely deliverable. We can recharter for something that might be more interesting to you.
A little bit more concretely, so we're jumping in. So we did have a bunch of site meetings with people who are unhappy with Rocky, for example, which is a non-IETF InfiniBand trade association technology for doing RDMA over 802.1 is the PFQ stuff, right? And there's DCQs in. But there's alternative proposal, and there's a desire to maybe come up with a solution for those type of Ethernet fabrics in the IETF, and that would work. That would be very interesting to see here, right? And that would need to be described in terms of what do you expect from your fabric, and then also what do you then can do at the congestion control level.
I look forward to that draft. Jeff.
Just ensure NVIDIA, so doing this on a daily basis. So there've been a couple of discussions and some spillovers from IPPM, but it doesn't work on internet. It's not meant to. There are specific use cases for data centers.
Yeah.
There's a number of congestion control mechanisms deployed today. So DCQCN is most well known as combination of ECN marking forward and PFC backwards, practically designed for storage, not really for like AI type of workloads. So due to replacement, due to improvements, there is, you know, what's going on in the industry with AI clusters. From like 1,000 GPUs last year, we went to 100,000 this year. So it's 100,000 endpoints talking to each other all the time, or at least most of the time, right? So special congestion control is very much needed. If your GPU is idle 20% of the time, you've just lost 20% of the value, right? So you'll see presentation on HPCC. There's similar efforts with different signals. Practically, we need something that's very fast, within order of 1 to 30 Ts, something that really makes difference in terms of how network behaves, whether they're done on the endpoints or NICs or on the switches. It's kind of secondary, but we are looking at the large ecosystem of things that need to happen, and I believe CCWG is the right place to do this.
Yeah, so this document does have some language about. Yeah, well, I broke things as usual.
I might just have to switch it back on.
Can I borrow your mic? This is not going to work in real time. Yeah, okay. I'll just grab it.
Yes, just grab it.
Okay. This is not good. This is not good video, but just briefly. So this document is intended to, and I think has language in it that says, you know, it's okay to standardize something that is not usable for the general internet, and you just need to state specifically, like, this is data center only or IoT only or whatever your case is. So hopefully that's well written, and you know, obviously we'll love any comments that help make that clearer. And yeah, I mean, certainly the CCWG charter has that absolutely in scope as it is today. Is it fixed? Thank you. So if there are no other comments, thank you very much. Look forward to your reviews.
Hang on, I would like to do a show of hands to see who has actually read the draft, also to remind everybody to join the Meet Echo if you haven't.
Very strategic. So no opinion means I am reading it right now. It is open on my window.
I think you've read more than 0 words. Well done.
One of the 2 recent revisions, maybe.
We might as well use the no opinion point, because I don't think, I think everyone has an opinion whether or not they've read it.
I hope so.
Yeah. Oh, but looks good. We have a bunch of people read it. We had a discussion. So yeah, let's give it a couple of weeks and then ship it.
Yeah, it's good. 12 is more than the reviews we got. So I'm glad we did that. Thank you, Reese.
All right, next up, we're going to talk a little bit about rate-limited senders. So one of the things that's worth thinking about here, and we'll talk about this a lot at the end of the meeting, is after we ship the BIS here, as we take on new work under our new guidelines for how to handle this type of work, we've got a number of presentations that we're all about to look at that are different areas in which we could choose to spend our time as a working group. So the questions that we want here are both, let's have some good discussion about the content, but also be keeping in the back of your mind, are these things that we'd want to consider as a place that we'd want to spend working group time actually moving forward and publishing documents? So with that, Corey, you are up. Feel free to request slides control if you don't have it yet. Oh, good. Thank you.
Okay. Oh, love the pan and tilt on the speaker's camera. That's cool. But I am learning how to do slide control. So let's go back to the beginning. Okay. So, right, I defer to Chair.
Sorry, Gory, I'm gonna just bring it back. I put everything in one slide deck. You literally just press the arrow to the right.
Yeah. Non-intuitive. Right, okay. This draft is one that originated with Michael Veltzel going to visit Tom Henderson and speak with him, and then I got involved slightly later. The reason for having this draft is because some people actually read the specs that are produced by the IETF. In this case, the NS3 community implemented exactly what was in the RFCs. And they did this. This is a plot of Seawind for an application or rate limited sender. The sender stops sending faster, and Seawind continues to grow and grow and grow, because the current TCP specs say you can do this. So I came and joined the crew because I'd worked on congestion window validation, but this is not the congestion window validation problem. This is simply a growing Seawind. So we'd like to fix this. We'd like to make a PS. We have an internet draft, and we'd like it to be adopted by the working group. But let's go on and explain a little bit more about the story. Next slide is here. What we're trying to do is write a couple of simple rules and basically restrict the size of Seawind that can be accumulated when you don't use it. The starting point for this is you don't actually want to say don't grow Seawind at all. Just keep it stuck at the size which you actually use, because that doesn't cope with transients and pacing. It's not a great idea. So you have to let Seawind grow above what flight size was, but how much do you let it grow? Maybe you should allow growing Seawind to 2 times flight size in slow start, which seems in general quite close to what was needed to make slow start behave normally when you have a bursty sender, and when the time which you put packets on the wire really depends on what the sender's busy doing otherwise, rather than what the arrival of ACKs are. So we propose 2 rules. One is must include a limit to the growth of Seawind when flight size is less than Seawind. And 2, it should limit the growth of Seawind when flight size is less than Seawind with an increment of max flight size. Right, let's cut to the next slide. When we did this, we thought, well, just a minute, what do people really do? And it was fun to have a look what Linux did, because Linux actually did what we hoped to, well, near enough. It had something that represented our second rule, and it's right there in the code. Oh, good. We don't need a proof of concept for the proposed new text. We actually have running code in Linux that does this already. But the RFCs are messy. Maybe we do need an RFC. 9438 says qubit doesn't increase Seawind when it is limited by the sending application or RWind. Kind of true. 9260, when Seawind is less than or equal to SS thresh, an SCTP endpoint must use a slow start algorithm to increase Seawind, etc. So we have something in the RFCs, but it's not that clear what exactly a sender should do. And we think it should be clear. We have in the appendix more confusion. There are several RFCs that almost touch on this topic. They don't quite say what to do, but they kind of hint it, and they are not quite consistent. So basically, we're asking, can we produce an RFC that actually clearly captures what a sender ought to do when they have a transient? Could we reformulate how a sender knows that the app is rate limited? I think that's probably useful. Or maybe just turn our rule number 2 into a must and actually declare a limit to the growth of sea wind when the flight size is less than sea wind with an increase of max FS. I guess we were hoping that people would give us feedback on what they thought was the right text. And we would hope to produce a small document. Current document's quite small, and just update the relevant RFCs. But that might include ones apart from TCP, of course, which is why we brought it to this working group, and perhaps could even comment on some of the other RM capped congestion controls, etc., which you just mentioned, if people wish to. Michael added multicast to the list here. I'm not so sure I'm so certain I know what to say with multicast, but if someone comes up with a good suggestion about how it's the same as other things, then that would be all right as well. So that's our talk. That's all we've got to say. I'll put back to this thing and ask the question. Well, I'll let the chairs get the right slide, and then we would like to take questions on this, and we have a queue. Christian.
Yeah, I am always uneasy when I see your document equating congestion control with sea wind, because there are a number of protocols that do not use the sea wind as the primary way to control the sending. The most obvious example is BBR, in which the sea wind is set to about twice what you need, because the limiting is done on the pacing rate. So basically, you set the pacing rate, that's your primary control variable, and you only use the sea wind as some kind of safety belt. So
Christian, did you Christian? Oh,
yes.
Sorry, there's a long delay between us.
Yeah, and so I'd like that when we do an RFC like that, we first explain in neutral term what the goal is, and then we decline that goal into what it does to the various control protocols that have been implemented. And you mentioned Rhino and Cubic. I would actually mention iStart as well, because iStart is very much in that category, and it's but the effects are not necessarily the same. So all these kind of documents, I'd like to separate the principles and the implementation. CWIN is the implementation; it's not the principle.
Yeah. Okay. I mean, the thing being that this proposes a small change to several RFCs that update them. They are defined in terms of sea wind.
No, I understand that.
And
that's fine. That's fine, Goey. That's fine. That's, I mean, clearly, if you say, and for Rhino, we shall change Rhino to do this and that, that's fine.
Yeah.
But there has to be a first principle before that says, you know, if you are basically not fully using your capacity, and you can measure that in various ways, then you shall not augment it. And that declines differently for different algorithms.
Does it? Does BBR do something different to this in reality? Is it not capped by 2?
I'll let Ian speak about that, because he's probably...
It depends slightly on the implementation, but in general, you need to be app limited either for the entire, non-app limited for the entire round, or for at least some portion of the round, in order to increase the rate typically, unless you happen to get a sample that's just straight up higher. But yeah, especially in the
upward growth phase. Yeah, there's quite a number of Apple checks, but they take into account that it's pacing, and so there's a number of ways of doing it, but like the point is you have to have some code that doesn't just check, are you using all the CWind? You have to have a check for like, have you been implemented? And it is a little more subtle, but obviously that's just the nature of BVR. For something like Reno and Cubic, it would be different. Or, well, actually our Reno and Cubic, I think it's the same thing too, because we also pace for those. So I don't know, anyway.
Ian, did you have a different question?
Sure. I think this is an important point. I think this should be written down somewhere. I think we should try to come to some sensible set of principles. I don't think they need to be overly prescriptive. Like, I don't think we necessarily need a number like 2 or something based on my experience with BVR and such, but I think we do need, like, the key thing is, like, are you app limited? Like, is the congestion controller sending as fast as it wants to send for some reasonable enough period of time that you think, you know, you're quote unquote using the pipe and exercising the congestion controller's ability to like detect if there's more bandwidth and such. So that's like the absolute critical thing in my mind. RFC 9002 has some text around this. It's not, I wouldn't say it's perfect. It's quite vague, but I think it's heading in more the right direction than not. So that's helpful. One question I have is, where does this belong? Like, does this belong in the document we just discussed, like 533 bis, as a general principle about like how congestion controllers should be made? No? Okay. Martin's like, I don't want to do it. I'm just asking this question. I don't know if this needs really, I think we should update these RFCs as we update them. I am not sure it's worth an update just for this one thing, I guess would be my thought.
Okay. The last thing I'd like to add then is that the motivation for updating in a separate RFC and doing updates is that it touches several RFCs. And so if we want to keep any of this in any consistent form, we probably would be well placed to write a document which actually does an updates line for the small bits of text in various places rather than wait for each of these to go for a document revision. I'm not sure we have appetite to update all these documents as a new BIS. So back to the chairs.
Thank you very much. All right, so for each of these, we're going to do a quick poll. So again, go scan that QR code, which was totally there a minute ago. There we go. And essentially what we're saying is, and this is a two-parter, but we're combining them in the interest of time. So we're saying this is something that we understand well enough to take on. And then is this something that we're actually interested in working on in this working group? And are we willing to contribute to that? So with that, we have a poll. Go click some buttons. None of this is deeply binding at this point. This is mostly just, as chairs, we're trying to gauge the interest of the working group and where we want to try to focus our time, because we have a large list of things we could do next, and it is very likely that we will end up doing most of those things. The question is, which of those things do we want to do first? Give that another few seconds, so go click buttons quickly. I see an Ian approaching the microphone. Slightly ahead of a Lars, who is not in the microphone.
Oh, are you?
Cool. Speak.
Okay. I was just saying I voted yes, but really what I think the question I was answering is this a problem worth addressing? And I think the answer is clearly yes. But I mean, how to address it is a more open question.
Very much yes. Thank you.
Lars, and I was actually talking to the bottom bullet that's still visible there. So we should remind ourselves that an option is also to declare something historic, because it doesn't have deployment. And for our MCAT, I think that's a pretty strong contender for just saying, rather than trying to update these documents, maybe we'll just say, you know, we tried that as a product of its time. It didn't pan out, and make it historic rather than like waste effort.
Carrying it forwards. Gotcha. Thank you.
Thank you all. I think we can close that poll now. Okay. Well, I think this brings us to Ingemar.
Okay, thanks. Hope you hear me well. And I guess we had a sound check at the beginning too. So I'm able to change the slide myself. Or we can take the next page here, and this is about the screen congestion control that has been around since 2015 or so, and it has undergone changes all the time since RFC 8298 was ready. And I'm going to present this, and I'm going to give some background about the use case that it has been mostly used for, and it's 4G and 5G networks that we have been using it on. And a little bit about the properties and cellular networks and 5G networks, and something about the video coders and quirks and faults that they possess, and then going into Scream version 2, and finally some bit of an experiment that we have been done, listing them up, and also the, actually the source code that has been evolving over time. And first we start with the 5G properties, and I'm not sure how well known this is, but you can take it in a way. And if you have a 5G network, you have if you take the simple case that you have one radio carrier, you have actually resource allocation in frequency and time, and that is typically evenly distributed among the users that are active for the moment. And if you have two users, then you split the resources 50-50 more or less. 3 users, and you split each user, get 33% and so on. But that is a resource, we call it the resource blocks. That itself doesn't really give a measure of the throughput that you actually get, because you have modulations and the coding schemes that varies with the channel quality, and in some cases you can have a power limitation in the uplink that also limits the actual throughput that you get. And this throughput can vary quite quickly, and it can vary on a millisecond scale, and typically get that for if you are close to your given throughput limit for the moment, you actually get some delay jitter that you need to. That is something that is given by the channel variations. And see like this. And to visualize this more, like I said, the picture on the upper hand, this is actually not the measured throughput, it's just a visualization of what it looks like. And as the cellular transport is subject to fast fading, for instance, and that means that the throughput can vary on a short time scale, and it can vary sometimes quite a lot. And in order to get low latency, for instance, for real-time application, you need to actually accept that the throughput that average throughput that you put through is a bit lower. So you have to pick one actually in typical case that if you want high throughput, you need to accept some queuing in the network, in the cellular network. If you want to have low latency, you need to accept a bit lower. And it's not can't give a really good numbers, but so today, for instance, if you move reasonably slow, you can have to accept that you have got 10 to 20% lower throughput on the average. If you move real fast, you need to have a larger headroom actually. And on top of that, you have actually something that's called dynamic uplink scheduling of intermittent data. And in typical case, for if you have real-time video encoders that you actually produce video frames of the even intervals for length instance every 20 milliseconds or so. And that means that in order to keep the queuing delay low in the network, you actually run out the data occasionally for a couple of milliseconds or so. That means that you don't have any data to transmit on uplink. And for the modem or the user equipment that we also call it, you need to actually send a scheduling request up to the base station. I want to have something today transmit, and then you typically get a grant, and it could be like just a couple of hundred bits that this scheduling grant indicates. And then you transmit data along with the buffer status report, and when the base station have received that buffer status report, that can indicate that you have like 50,000 bits to transmit. Then you get a grant that is picked according to the channel capacity and the throughput allocation, or the resource allocation that you have for the moment. So that this ping pong is a couple of times before we have transmitted your data. And the effect of that is actually get some increased delay actually in the transmission, because you need to send a scheduling request first, and you get a grant, and you get a buffer status reports and that stuff. So, and also it can give a reduced link utilization, because you actually underutilize your first scheduling or your first transmission opportunities. And you can also have additional delay due to congestion, of course. Scheduling, handover, it can either increase because you get a gap in the transmission in typical case, and also some battery saving functions like discontinuous reception, DRX. And also, of course, retransmission on lower radio protocol stack layer. And then you have transmission on the MAC layer. You can occasionally have retransmission on the RLC layer as well. So this is the kind of reality, cellular network reality that you have to address when you design your congestion control for that. Okay, and video coders, they have lived their life on their own. And one case that people frequently talk about it, the iframes can be really large. And iframes are a pain. And for that purpose, in order to, if you're close to your network capacity limit, it's actually highly recommended to use something that's called a gradual decoding refresh, because that will spread out the iframes in some sense, and it makes your congestion control easier to manage, because you don't have iframes that can be like a factor 5 to 10 times larger than the nominal frame size. And also importantly is that the P frames vary in size. If you have, for instance, if you have remote control car and you're for instance steer right to left or something like that, and actually the temporal bitrate can change quite a lot. And this means that in order to cope with the varying frame size, you actually need to give your congestion control a bit on additional headroom to avoid that you get increased queue and delay for the cases where the frames are become larger. And this is visualized in the graph below. You have the frames 1 to 7 that are varying frame sizes, and you should ideally be able to transmit one frame before the new frame is generated, regardless you use packet pacing or not. And as a reference to the earlier presentation, yes, the video encoder typically you have a maximum bitrate, and the congestion control then becomes application limited. And if you have a 5G networks and sometimes can have like 100 megabit per second throughput in the uplink if you're alone in the cell. You can be pretty often application limited actually, and experience congestion when you run out in a poor coverage, or you have an increase of number of users in the cell. And finally, here in this context, we have some odd features that we have discovered, and you can have a systematic error in output rate. When you ask the video coder to produce video at 20 megabit per second, you might actually get 25 megabit per second from the video encoder. So you need to cope with that also. And some video encoders can be sluggish, which means that if you request a reduced video bitrate, you actually may not get that because you have internal rate control loops in a video encoder that can make it take 200 milliseconds for the video to stabilize. And in some special cases, and hopefully historic cases, some video coders cannot change the bitrate until the next iframe or a group of pictures, it's also called. And they're not really ideal for real-time media if you want to have a congestion control later one. But slightly sluggish rate control can still work. And when it comes to the Scream version 2, and I'm not sure if it's Scream, that actually stands for self-clocked rate adaptation for multimedia. And it was an RFC in 2000, I don't remember anymore, but 2017, 18 or something like that. And it has, since that, it has been updated several times. So after a couple of years, you didn't recognize the original RFC 8298 in the running code that has been public since then. And recently it has been simplified quite a lot, and it's actually now a lot easier to understand what is actually happening under the hood, because the older version had contained some, what I would say, like magic wands that did things that it's more like sometimes spaghetti hacks to fix certain issues. And also L4S was originally patched in somehow in the code, and now it's more designed into the actual congestion control. And a lot of work has been actually on working, getting it working with L4S, and because delay-based congestion control, that is one part, is that you only get, given the delay properties that we have in networks, not only cellular networks, but otherwise, it's really hard to get the delay-based control and congestion control work well. There are so many different degrees of freedom in how delay is. L4S gives some kind of a more confined signal that you can use and utilize. And a bonus, if this becomes accepted as a working group item and finally later on an RFC, that can actually provide hopefully some kind of a best current practice on how to do congestion control for multimedia. And if you go into the congestion control, it's based on one-way delay, similar to the old LEDVAT, packet loss detection, classic ECN, and L4S, and they work some kind of in concert, at least with if you have a delay-based packet loss on L4S or delay-based packet loss or classic ECN. So when, for instance, L4S doesn't work, you don't get any packet marks, but you still have see that the queues are built up, and then you rely on delay-based congestion control or packet loss. So it's not like a mode switching or something like this in a broader sense. And one important thing here is that the transmission control, it doesn't impose a strict limit on the bytes in flight. It's more like a soft limit. You can exceed the congestion control limit. And the rationale behind this is that you actually make the video rate or media rate more stable. And but still you have congestion window as a kind of a circuit breaker when things go wrong, and if you, for instance, if you lose feedback or something like that. And the media bait rate is actually based on a simple relation between congestion window and RTT, with some variations that I will explain later. The packet pacing is done faster than the media bait rate all the time. And importantly here is the congestion window validation that is very needed in this case. For instance, if you go for a rate limited scenario to a throughput limited scenario. The feedback is RFC 8888, and it's quite useful in that case. but just still only 5 minutes left. And the congestion window update. You have a update maximum once per RTT on the left-hand side if you have packet loss, or if you have a delay-based, an increased delay. And the delay-based congestion control is some kind of virtual or LFRS marking. And when you exceed the target delay divided by 2, you start to virtually mark packets. So for that, in that purpose, but you have the target delay, and that is a bit higher than there could be a target delay is like 60 milliseconds to cope with a clock drift, for instance, and sometimes you have clock skipping, so you can't tune that too narrow. So because you don't want to overreact based on real life issues like clock drift, and also you don't want to overreact on non-congestion events that can be quite frequent in some cases. Then we have a LFRS-based control, and it's very much like how Prague does it. And actually, in addition, if you have very small congestion window, congestion window in terms of packets, you actually limit your reduction. And that is actually complemented if you with the increase of the congestion windows. If you have very small congestion window, you actually limit the increase, and that makes it more stable at the very small congestion windows. And as I said, it's on the right hand side. If you always try to increase your congestion window, and on top of that, if you are uncongested for a longer time, you actually have this multiplicative increase function. And also for if your non-LFRS is not working, you stabilize your congestion window with an inflection point. It makes things a bit more stable. The target bitrate update is based on a simple relation between the congestion window and the RTT. And on top of that, you actually need to downscale a bit more if you have largely varying frame sizes. That makes things a bit more stable. And also some extra if you don't have LFRS working, you actually need to scale down a bit more if you have a burst in flight that exceeds the congestion window. That makes the control system a bit more stable. We can take the next slide here. And this is an example of if you don't have LFRS working, or if you have LFRS working, and you actually get more stable throughput and actually the network latency. And also important here is that the burst in flight is red one can exceed the congestion window.
Quick time check. You've got about 6 slides left and about 120 seconds. So it may be worth picking a few that you think will promote the best discussion.
Speed up a bit. Yeah. And we have a multiplicative increase that makes it possible to increase your ramp up to a higher link capacity if that increases. So packet pacing default is like 50% higher, but if you have large frames, then you can actually speed up a bit more to being able to empty the transmission buffer quickly. Congestion window validation, that kicks in if you are rate limited more or less, but you still have this if you have what you call slow start or whatever you call it, you can actually increase by, in this case, up to 2 times the burst of flight. Some sources, and the scheme has been developed since March 2015, and it's been continuously. There are some code that you have a test application that is more like a plumber say that is been used quite a lot when they have developed L4S and other aspects. And you have some multi-camera functions here with a complete key stream with multi-camera support also. And some experimentation that we have done. We have this large demo on Mobile World Congress that good support up to 4 cameras, And there's some cloud render gaming demo that if you can look at when it's on the wish list, actually to get support in WebRTC. So then this is an example from the Mobile World Congress demo on YouTube. Yeah. Impact well for us more or less. So okay, I believe I'm right in time. I guess with a bit of a hurry in the end too.
All right, since we are at time, if you want to jump in the queue, now is the time to jump before we close it, and otherwise we will start our poll momentarily. So go fast, Ian.
Yeah, also thank you, Ingemar. This was a great introduction to Media CC for a room full of people who might not all have the same context. Now, Ian?
Yeah, no, this does look really nice, and thanks for all the explanation. I have one kind of pedantic nit, which is calling it Seawind and then saying that it can go above it is sort of like blowing my mind right now. And I get like what you're trying to convey. Like from an algorithmic perspective, I have no concerns about the implementation and that it works. But like maybe we need another variable because there's no, at least typically the concept of max bytes in flight exists. Usually Seawind is that the limit on that thing. So maybe if we could come up with another name for ideal bytes in flight, I don't know. I'm not sure. I don't really care. But like that's sort of every time I heard it, I'm like, wait, what does this word mean anymore?
So you want to respond to that one, Igor?
I'm not sure if I got the question on it, to be honest.
Oh, it's okay.
Yeah.
There was no question. There was just like an idea, like because I also saw that condition window and then blowing it up. I was like, kind of like, okay, what's going on? So maybe you need to say like what to do about it. But previously you show some results. Like, did you really? So how is the Scream version 1 like Scream working on the same kind of scenario? I mean, can we get some comparison like how Scream is doing and Scream version 2 is doing in the same scenario?
How a comparison between
Scream and Scream version 2, like just to see like we understand like how much we're gaining by
I believe perhaps some answer is given here. Actually, one flaw with the earlier versions of Scream is that this is actually this demo. We still didn't have a version 2, so you can see, for instance, the congestion window. That at that time it was like a harder limit, but you need to blow up the congestion window a bit more to cope with the varying feature. And the change it now that you keep it as a soft limit and you do more strict what's called validation of the window to be more adapted to the thing in case where the throughput drops or you go from an application limited state to a non-application limited state. So that is a large difference. And on top of that, then the computation of the video rate is much more simple and more stable and more comprehensible.
Okay, so it's a combination of an implementation gain that we learn,
yeah,
and also like the new kind of like congestion indicators that we have.
Yeah,
that makes the
exactly.
Okay.
Yeah,
okay.
That's pretty much a repair of past mistakes. So,
all right, Gory.
Thanks, Ingemar, for bringing this here. This is really interesting, and I enjoyed the talk. I was going to come back with a similar thing to Ian. I think Seawind is a limit to the maximum number of bytes in flight. So how can target rate go above that? But maybe this is just a wording thing, as you explained. But I wondered if you wanted to say something.
I know perhaps one should rename to something else than a congestion window, because as I understand, it can cause confusion in the audience. So I'm not sure what it should be, but
I'm sure people can help with that. I don't think we need to take up working group time to discuss it. I love the talk. Thanks ever so much for bringing it.
Abhishek?
Abhishek, a couple of questions. One is the results on L4S on off, were they on a cellular network where the congestion indication was being added at the scheduler? That's question one.
Yeah.
And second is I saw a mention of moving to 75% on an operating point if the relative variation in frame size between I and P frames is large. So my question there is on a real-time video stream, how do you know this beforehand when the feed is coming in and the encoder is working? So do you know this beforehand? What would be the relative variation of your I frames and P frame sizes?
Okay, can take the first question. In this case, it's a very simple wireline bottlenecks actually with an AQM that does L4S marking or not, and we have picked, I believe, so like in this case it's like a 4 millisecond queue delay when you start to mark packets, but it can be a dual queue AQM as well. And in the second, and I mean for cellular, you actually do the congestion in the detection on the lower layers than what you mark on the PDCP layer. So and as for the this is actually based on you compute a histogram on the frame sizes. And it's a leaky histogram, so if your video properties change over time, you actually get a new histogram. It's relatively simple implementation. And it's not documented in RFC, but perhaps it should be a bit. I believe it's somewhat documented in the proposed RFC or the draft. But so, okay, hope that they answer the question.
Thank you all for the comments. So for a quick poll on this, thank you, Ian, for some of our wording updates. We liked this better. So this is something that's worth addressing, and the working group should take this on. So again, this is a help us prioritize. What do we think we want to talk about first? Is this something that we shouldn't be talking about at all? Is this something that we want to spend some time on? I know we've talked a little bit about how we want to handle congestion control for media-related things, and we'll talk a little bit more about that at the end of the session. But go scan some QR codes if you haven't scanned them yet. We'll leave this open for a minute while we get set up for the next. All right. Thank you all. And next up, we're going to talk a little bit about HPCC++.
Okay, Rui, the floor is yours. You should have control of the slides.
Okay, got it. So since people talk about the data center congestion control, so this is a proposal we have to address this issue. First, we talk because we present this idea in the previous IETF. So this time we will give a very quick recap on our basic idea, and also we want to provide our deployment experience and more test results. First of all, we want to recap on the scenario we're targeting. So this congestion control, we're targeting for data center applications. So a typical emerging data center applications like storage, database, and machine learning applications all require network communications. So for example, those storage applications, when users send a request, those requests actually being spread to multiple servers, and all the server need to respond based on the part of the request, and then user can only get a reply once they aggregate all the results. And that latency actually and throughput also become very important. And also for machine learning applications, and today we have 10,000 GPU training that the 10,000 nodes need to communicate. And this number keep growing to 100,000 this year. So which means that all the nodes need to communicate and synchronize typically hundreds times within a second. So if any node gets slow, then the whole job will get stuck and wait for their to finish it so they can start next iteration. So just give this idea how important data communication will be in the data center scenarios for those emerging applications. So in data center, we have those very fast transport layer. For example, like RDMA, they can allow the client to send the traffic in a line rate, actually. So the issue becomes like you cannot allow all the senders send the traffic arbitrarily, then without any orchestration. So that's very bad for the network. So that congestion control actually become very important in this scenario to schedule the communication across multiple senders so they can coordinate. So traditional congestion control previously we use mostly for internet that actually rely on heuristics. So for example, if you see the packet loss and then you guess probably there's a congestion in the network, you will reduce the sending rate, but you don't actually know how much you need to reduce. Some guess it will be there, like you can cut the throughput by half, something like that, right? So in the early stage in data center, we also rely on something like ECN to notify, and only a single bit that only provide very limited information. So the whole idea of HPCC is, can we rely on some precise information that we can get from network? So based on those precise information, the sender know exactly how much they need to reduce, but also they will know how much exactly they can increase. So hopefully we have this capability in our today's hardware. Today, the network switching ASIC provide this in-band telemetry information and also supported by many vendors. So here shows the basic idea. When the packet goes through the path, each switch along the path can attach the telemetry information into the packet headers and all the way to the receiver, and the receiver send the reply back to the sender. And the sender, based on this telemetry information, to adjust the sending rates. Those telemetry information including what's the link bandwidth, what's current queue length in terms of bytes, and also how many bytes that link are already being sent. So the sender can calculate exactly what's the utilization of the link. If it's overutilized, how much we can reduce or increase the bandwidth precisely. So that's a basic idea. Doing so, we have a couple of benefits. First, we can achieve very fast convergence, typically just one round trip time. We don't have to use heuristic to adjust the rate like across multiple round trip time. We just directly jump to the correct sending rate within one round trip time. And then we can potentially maintain a near zero queue because those feedback doesn't rely on any queue buildup because that would be too late. Then we can literally maintain zero. We will show some results later slides. And the last, we only have a few parameters because we don't run any heuristic. We know precisely what's the current status of the network, and which help our parameter tuning and also maintenance of our network. We have two proposals for this specific idea. One is the standard draft to talk about the algorithm. So that we talk about how we can use what telemetry information we want to use, and how we're going to use it. And we believe congestion control is a service. They can plug it into any transport protocol. You can plug into RDMA or TCP if you like. It's just your choice. But basically, we see congestion control is a service you can leverage. And the second proposal is more about the packet format and how you can encode telemetry information into the packet. Right now we have a support those three format, but we can extend to many other format as well. And here we show our deployment experience. Today we have deployed HPCC to storage, AI training, and the database application in one of the major cloud providers. So this diagram shows that the typical storage application is a elastic block storage. When the user generates requests, this request actually being spread to many storage server, and then the user can only get a response once all the servers send a response. So in these scenarios, network communication become very critical. If you have one straggler and get delay, and all the requests will get delay. So by using HPCC, we actually increase the both throughput and also reduce the latency significantly. That's the experience we found. This congestion control is very helpful for this data center application. And we also did an extensive experience testing in both hardware-based implementation and also in simulation as well. So this figure shows the hardware results. We compare with DCQC. So DCQC is the congestion control used primarily in RDMA. It relies on ECN as a signal to indicate congestion. So we compare the performance in 99th percentile flow completion time across multiple different flow sizes. We can show that across different flow sizes, we can achieve up to 95% latency reduction in the small flows. And the figure in the right show that queue buildup in our experiment. We can see that DCQC actually have a long tail distribution in the queue length, while in our case we nearly maintain near zero queue. Basically, you don't have to maintain queue in the network. We can see there's only 23 kilobytes in the 99th percentile, which translates to only 7 microsecond queuing delay across the entire experiment we have. We also did more extensive experiments and evaluation in our simulation to compare with other congestion control mechanism. Because we don't have a hardware implementation for each of them, we compare them in simulation. We show that HPCC plus can actually outperform those different congestion control algorithms. Yeah, so that's all for today's presentation. So we highly appreciate your feedback, and feel free to contact us if you have more questions.
All right, great. Thank you, Rui. Does anybody have any questions or comments now? We have a few minutes. Xiaomin?
Hi, Xiaomin from ZTE. I have a question about your HPCC info draft. In that draft, you provide 3 options for the congestion notification, right? So INT, IFA, and IOM.
Yes.
So for the 3 options, do you have any comparison? is there similar in the performance about the HPCC?
So those format are just the way you can encode the information into the packet, and the information actually will be the same across all the different format. I mean, they may have some difference in accuracy, like some format may have 8 bits, some format may have 10 bits, something like that. But the point is that you capture the necessary information we specify in the algorithm, so that you can run the algorithm correctly. So that's why we think the performance will be the same across different format, but they're just a different vendor. They have their flexibility to choose which format to support, and that format is orthogonal to the algorithm we propose. So that's why we want to decouple this dependency so that we can make two different draft for the purpose.
So have you tested all the 3 options in your testing?
We have deployed and tested some of them, but not all of them. But that should be our future work to test the performance across all the formats. That's a good point.
Yes, as I understand it, the 3 options they use different layer to encode the format you provide. So maybe they have different performance. Performance. Yeah. So I think if you have any test result, that's great. And if you can show us, yeah.
That sounds good. Yeah. Thanks for the feedback.
Okay, Lawrence.
Lawrence Stewart, Netflix. Hi, Rowie. I was wondering if you could speak to whether the switching fabric you were using here did virtual output queuing or was using sort of regular queuing.
I think that's the way the switch using queuing mechanism actually is independent or orthogonal to the algorithm. But the key point is that switching may have multiple queues. And then if you support multiple queues, especially for those virtual queuing stuff, and then if you have traffic in other queues, then the congestion control become more complex to support this multiple queuing. And we actually, in our draft, we have a proposal or algorithm design to address that. That will be part of our work as well.
Thank you.
All right. Thank you, Rui. Same question as we've been asking all along. So this is a problem that is worth addressing, and the working group should take this on. So again, this is one of those things where we're looking to gauge the order in which we tackle things and what there's interest in pursuing. We'll talk a little bit more about criteria and deployment thresholds and things like that in a little bit. So right now, this is mostly just what are we interested in? Where do we think there's problems that we need to solve? Do we have the right expertise in doing that? And while we're doing this, let's get set up for jump all the way through. Next up, we're going to talk about some BBR.
Would you like me to go ahead and start, or are we doing? Okay, great. So thank you. Yeah, so my name is Neil Cardwell, and I'm going to be talking about BBR version 3, a sort of lightning fast algorithm overview, since we've talked about it before, and then just a quick update on the deployment status. And this is joint work with the BBR team at Google, which is composed of the TCP folks and Quick folks. And then let me try the next page. Yes, that works. Okay, so I'll just start with the overview, talk about deployment status and plans. And the goal here was basically just to respond to a request from the chairs for a quick refresher and overview. And, you know, and we're inviting folks to offer feedback on what kind of plan makes sense for you know, whether we want to pursue a working group item and, you know, further documents for BBR. So if we had to describe BBR version 3 in a nutshell, I think we could say that the design goals are basically number one, to be able to achieve high throughput, even with some targeted level of random packet loss. We also, number two, want to be able to bound the amount of queuing delay that we have, even if the bottleneck buffer happens to be quite large. And then third, we want to have some sort of usable coexistence story when sharing a bottleneck with Reno or Cubic congestion control. And the basic mechanisms that we're using here are a model-based approach where the algorithm dynamically probes the network path and then builds an explicit model of it, where the main parameters are the maximum recently observed delivery bandwidth, the minimum round trip time recently seen, the maximum degree of aggregation that has been measured recently, and then the maximum amount of data that we've been able to put in flight and then get delivered without experiencing too much ECN or loss in return. And as you could guess from those model parameters, the signals we're using are basically bandwidth and round trip time, as well as ECN and loss. And here the ECN flavor is a shallow threshold ECN like DC-TCP or L4S. So just to give a sort of quick architectural picture to have in mind when you're thinking about the algorithm, this is kind of the way that we think about it. The algorithm takes as inputs, you know, these signals that we've been talking about, feeds them into the model, and then the model generates its estimates for the various parameters we just mentioned. And then those go into a probing state machine that makes decisions about speeding up and slowing down to sort of explore the network and try to find a decent operating point. And then the output of those decisions is basically three control parameters: the pacing rate, the congestion window, and what we could call the quantum or burst size for any offload mechanisms that are in use at the sender, such as in the Linux ecosystem, they're called TSO and GSO. And then those three control parameters go into the pacing engine, which takes the stream of input data bytes from the application in the form of socket writes or send message calls, and then chops those up into MTU-sized packets and then paces those out onto the wire. So just a quick overview of the various versions of BBR that we've talked about in the past, and you may see references to. There was BBR v1, which is the original back in 2016, 2017. Then there was version 2, which we talked about and open sourced in 2019. And then version 3, which we talked about and open sourced last summer, last July. And then there's also BBR Swift, which is a version of a BBR that we use inside the data center, which is using an estimated network round trip time as the main congestion signal. And that's something that we just use inside data centers at Google, where that extra signal is available because of the what we know about the expected round trip time within a data center. You know, here we probably don't need to spend that much time because we've sort of talked about this implicitly, and folks are pretty familiar with Cubic. So in the interest of time, I think we can skip this, and folks who are interested in the direct comparison can kind of take a look at the slides. And then in terms of the deployment status, it's pretty similar to what we discussed last July. BBR v3 is used for all of our internal WAN traffic for TCP. BBR Swift is used for the TCP traffic that's within a data center. For Google external traffic, that is TCP. We use BBR v3 for both google.com and now recently YouTube public internet traffic. And then on the quick side, there's a quick implementation, and that's currently under A/B testing for a small percentage of users. Yeah, so we've done an open source release. Here's a link for the TCP implementation on GitHub. And as time becomes available, and our team unfortunately has a number of other priorities that we have to work on, but as time becomes available, we plan as soon as possible to replace the Linux TCP BBR version 1 code with this v3 module. And the motivation there is that we think that makes sense, given that it has better coexistence behavior with Reno and Cubic, which is an important goal. It gives us lower loss rates, provides actually lower latency for short web requests and starting video streams, probably because of the lower loss rates, while also having throughput that's pretty similar to BBR version 1. And so here are some links to the internet drafts, which unfortunately still reflect version 2. The differences between v2 and v3 are relatively minor. So there's, if you're interested in reading them, it's still, your time would not be wasted. And then, we're always looking for feedback, obviously. I think I do want to say that I think a BBR is sort of a work in progress, and there are definitely a number of ways it could be improved. And so, to be honest, my initial inclination thus far has been, rather than spending time polishing the document, to try to focus time and energy on improving the algorithm or coming up with better algorithms. But that said, I gather there might be interest in moving a document forward. So if that's going to happen, I would definitely like to be involved. So yeah, thanks for listening. Appreciate it.
Thank you so much, Neil, for refreshing our memory and sharing some exciting deployment updates. We have a queue, and Ingemar is first.
Okay, I happen to be first. Thanks. One question about this 2%. Is it based on some kind of empirical studies that you pick 2%? Because 2% can mean quite the difference between, depending on the bandwidth delay product.
Right. No, it's been based on our experiences, both on YouTube and Google.com and our internal WAN. Obviously, if we're going to turn this document into something, a working group item, obviously I expect that particular magic number will receive a fair amount of attention, and we can put some more science and engineering into it. It's basically, that is, if you're talking about the time scale over which that's measured, that's over a single round trip time. And so the average loss rate that's generated is typically much lower than that. But that's sort of the maximum that is willing to tolerate over the time scale of a single round trip. Does that answer the question?
Yeah. Perhaps one more, if I'm allowed, or should I get? Yeah, I believe you mentioned for us, is it still limited? Like you have the BBR version 2, you had like 5 millisecond limit before using this low latency, or is that lifted, or is it to allow for other qualities?
Right. That magic number is still in the code, and within Google, we've only been using the ECN support at low RTTs. And I think for using shallow threshold ECN over the public internet, I think that should probably happen in the context of doing something that's coexists well with Prague, and that support is not in the code at the moment.
Thanks.
All right, Martin.
Martin Duke, Google. Neil, can you speak at all to your knowledge of what Google entities are using BBR. Any version of BBR really? Or
Yeah, so others can chime in here. Off the top of my head, I think Amazon's cloud CDN uses BBR v1. I think Akamai uses BBR, some version of BBR for a significant percentage of their traffic. I'm not sure if it's v1 or v2 at this point. I think Dropbox uses BBR v2. I'm sure there are some Meta folks in the room who could chime in on whether and how it's used. Yeah.
Cool. Yeah, that's a lot, and the fact that all these different versions maybe to me is a compelling argument to standardize this. Thanks.
Okay.
All right.
Alessandro
Cool.
Ghedini, Cloudflare. To Martin's questions, we also use BBR for TCP, and we're sort of going through the paces of trying to implement that for our quick stack. And something that we've sort of discovered is one thing is defining the BBR algorithm in the draft, and another thing is actually implementing it and making it performant. And there's a number of situations where we've had to sort of go and try to reverse engineer the Linux implementation to figure out some of the gotchas and implementation details that are probably not that uncommon to other people. So I would definitely be interested in seeing like the working group work on the BBR the BBR algorithm itself, but also figure out what sort of work we need to do to actually be able to implement it properly and make sure that we don't deploy some broken implementations on the internet. I do have a question about the Linux patches. So you said you're gonna replace the current BBR v1 in Linux upstream, which I think makes sense. But it would also be useful to keep having the out of three changes with both BBR v3 and BBR v1 to be able to sort of test it better, like compare. So I was wondering, do you have any thoughts on whether you will be able to maintain that out of three fork going forward for some period of time?
I think we could do that. You mean as a sort of out of tree, something on GitHub or something that has the old BBR v1 code for folks that want to do A/B testing on large sites? Is that what you had in mind?
Yeah, basically, I mean,
Okay.
we could deploy our own, Linux patches, and ideally we wouldn't, maintain that patch ourselves. I imagine some other folks might be interested in the same kind of changes.
Right. Okay.
Okay, Cullen.
Cullen Jennings. So this is largely with work that's in the context of the mock working group where we're doing media over Quick. But we're using this a lot, and this is work that Cisco's doing in conjunction with Christian Huitema. I'm really interested in what sort of results you're seeing or what sort of testing is being done on particularly Wi-Fi and the type of network characteristics you have over Wi-Fi. Has that been a focus? And can you say a bit more about that, how we've done that?
Yeah, that's definitely was a focus at one point. We talked about that work. I think it was IETF 101, I want to say. I think that was, I want to say, does have its maximum aggregation estimate, which is particularly important for Wi-Fi, but is also relevant for cellular and DOCSIS cases, which also have significant aggregation. Yeah.
There's a chance that you're not getting any audio from us.
Yes. Oops. I was not getting any audio. Let me I see someone's pinging me on chat. Let me find that tab.
Neil, I can hear you.
We'll ask Meet Echo to help with that.
Community rather than
yeah. Okay,
questions
I'll
for
make
Neil.
one comment to the community here then, which is like, I mean, like I find it shocking given the huge deployment and all the stuff going on in this that's not already a working group draft. I think we should adopt this and figure out what we need to do to fix it for sure. Thanks.
And that's showing up in the transcript, so we may be good. Go ahead, Matt.
Now here, Neil.
Can you guys hear me?
Success.
Okay. Yeah, I hit the reset button.
Is there anything sage from what you were saying that you want to repeat before I start my question? Or
I don't know where I cut off, so I'll just let you go ahead.
okay, so to the question about deployment, I was conveniently in queue. Meta uses BBR v1-ish with our quick deployment, which is the vast majority of our egress traffic, and then the rest of our internet traffic uses BBR v1 in Linux with TCP. And we are currently working on what maybe is like BBR v2.5 plus some other stuff in our quick implementation, and we're experimenting with it. So we're working on that, and we, echoing what Colin said, is that we think that this should be something that the working group works on, and we are happy to lend support to that in terms of, you know, editorial work and things of that nature.
Great.
Mosinati Cisco. To echo what Colin said, we're experimenting with this in Media over Quick, and we've tested BBR v3. It's performing better than v2 in our experiments, but we still have a lot of impedance mismatches with media. And so I'm wondering, when you said it's on by default now for YouTube traffic, is that only VOD YouTube, or does that include YouTube Live or YouTube TV or anything that's more real time or latency critical? And are you testing for media apps specifically and making design changes for media apps specifically, or are you trying to model media apps as just you know, typical elephant flows?
As far as I'm aware, BBR is used for all of the YouTube TCP connections, and I guess I'm not. Maybe Ian actually could speak to what transports are used for some of those live services. And in terms of testing, I mean, I think again, Ian has done some work in this area, but I think our experience has been that BBR is not great for real-time stuff because it was never sort of designed for that. We have ideas about how it could be improved to make it a better fit for real-time stuff, but haven't deployed anything like that.
So in terms of YouTube, all products I can think of that are user-facing serving would be TCP or quick BBR. That would certainly include TV and all those things. Ingestion, we do, I guess, like 5 different ingestion protocols, like WebRTC, the whole, whatever someone wants. So that's kind of a different ball of wax, and obviously a client's congestion controller is what it is. But for delivery, I can't think of a single thing that's not some variant of BBR. Oh yeah, and on the real-time stuff, yes, there are challenges with BBR. Most of them are around the app-limited nature of it. And that's kind of the critical challenge.
Well, we'd love to see it adopted and be able to contribute some of the changes that we're considering for media and app limited flows, because rather than having Scream and something else and 5 or 10 different rate controls for different applications, it'd be better if we had a common rate control that worked well for most applications.
Beautiful, thank you. All right. Time to click some buttons again. Everybody race into your browser of choice. Same question. This is a problem worth addressing, and the working group should take this on. Thank you, Neil. And Thank you all for some of the really good feedback and comments as well. It sounds like we've got a wide variety of people who have either deployed or are interested in deploying and may have some learnings that would be great to talk about and share. With that, let's talk a little bit about where we go next. I see we've got a no vote in here as well. Would anybody who said no like to come to the mic?
I didn't say, I said yes, but I put a sort of snarky comment in the last snarky comment in the chat that it's not so snarky after all. So the first step to standardize something or work on something here is to get rid of some of these versions and options and plus and merge this and others. So I'm really interested in BBR. We definitely should be doing this in this space. It's the right group for it, no question. But the plethora of variants is making it real hard to understand, you know, what's working, what isn't working. And the way I understood Neil is that at least in Google, it seems to be they really at least strongly like deprecating V1 because they were like putting V3 in the Linux kernel. And so maybe if we could all agree that maybe we'll sort of focus ourselves on at least on the V3-ish variants, that would make me slightly happier. But it's a proposal, but I'm just confused because I don't follow BBR that closely to actually know what all these differences are. And thanks.
Thank you. All right, I grabbed a microphone that I don't have to eat quite as much. Let's talk a little bit about next steps here for CCWG. So extra thanks to our authors and editors for the BIS document. As we wrap that up, we believe that we've defined a new set of criteria and processes for what it takes to specify congestion control within the IETF. And a big part of the group, and we've been talking about this the whole time, is to make this a space where we can actually make progress that is significantly less painful than some of the previous efforts. We've got some text on here, which you're welcome to read in your copious amounts of free time. But essentially, we want to make sure that we're specifying congestion controllers so that people can interoperate. And interoperate is kind of a weird term here because, of course, what I choose to do on my client both does and does not impact those around me. So that's been always a challenge and is going to be a fine line that we're going to be walking. What that tends to boil down to is we've got two criteria that we've been talking about and proposing. And this is essentially part of how we discuss what venue we want to bring different documents to. So this is, do we have empirical evidence of safety? Is this going to harm others? Is this going to prevent others from being able to interoperate? And then the second one is, do we have a stated intent to deploy by major implementations? And you'll notice that that is a plural word. So this is both a, can we take things and make sure that we don't make anything worse? And also, are we putting our time and energy into something that should be a standard and where the people actually are? So we have a little bit of a litmus test and some interesting questions to ask ourselves for each piece of new work. And we've been working very closely and in some cases in the mirror with the chairs of ICCRG as well as others around the IETF and IRTF to talk about where do different documents belong, where do different talks belong. And the informal version of that is right now we're thinking of ICCRG as an incubation place. So we take different experimental work, we take things that we're doing research into where we have a lab and we're testing some stuff and we want some feedback. And we have a wonderful group of experts, many of whom are also in this room, to talk about, you know, hey, did you try tuning this in this different way, or did you take this signal into account? We then also have CCWG as a place where we can have those same conversations in a direction towards let's actually publish standards for those who have significant deployment and are demonstrably safe. What that's turned into is this nicely colored set of boxes, which are essentially, there are potential to have, starting on the right, we have the independent stream editor, and we can potentially publish algorithms that aren't going to change based on IETF review, right? And so this is review for some of you. But if we have a thing where we want to say, yep, and this is what my implementation does, and this is what I called it, and it would benefit others to be able to see it and review it and understand how I'm going to behave on your network, there is a place for that. If we are willing to update based on IETF and IRTF review, then we have both the CCWG and ICCRG. And so we have kind of, for less mature documents in places where we're incubating new work, new research, things like that, We discuss that in ICCRG, and at some point we graduate from that when we've actually proved safety and when we have ideally data from major deployments already, but at the very least stated intent to deploy. Then we start talking about, can we move some of these things more towards standards? So I see Lars hopped in the queue. Is that a clarification question? Yeah, cool.
Yeah, so so I reacted because you said we can put stuff on the independent stream and we actually can't. It's up to the independent stream editor. And
yes.
So the proponents of a congestion control scheme can choose to take their thing directly to the ISE and get an RFC number, and the working group need not even hear about it, right? I think if the working group decides to publish something, it is possible to publish something for posterity on the IRTF and IETF stream, where we have plenty of documents that say, Microsoft's blah, 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 or Comcast Congestion Control Manager, or something where we at least believe that whatever they're doing is interesting enough that, we want to make sure that the description has been written such that it's understandable. And we can choose to publish that through the working group if we want to. And I thank you for AD's past, present, and future that you didn't put the AD sponsored route up there, because we should not use that.
Thank you. Yeah, that is a very good clarification. That was an extremely broad we here. But yes, the we that is in this room have paths towards publishing experimental and informational documents and other things of that sort as well, that aren't just the independent stream editor. And you can, of course, hop directly there without talking to anybody else.
Yeah, Reese Enghart with my ICCRG chair hat on. ICCRG can totally have presentations on algorithms that are in CCWG, right? There's nothing stopping us from accepting like a researchy presentation on BBR in ICCRG. Just wanted to clarify that.
Yeah. So another big part of that is this also means that you get to have more than 1 2-hour block in an IETF week where you get to think about and talk about with awesome congestion control concepts with other people who are also similarly awesome. But a big part of that means that we're coordinating very closely as we kind of build out agendas to make sure that we're doing something sensible and sane. So we would also love feedback on that if you've gone to both, say, this morning and right now, and you're like, wow, that second part was a complete waste of time because I saw it all in the first part. Come talk to us, and we'd love to know that. So that brings us to kind of where do we want to go next? As we've been talking about future work, and this comes back to what we've been saying the whole time, a big part of this is, can we talk about new congestion control algorithms and standardizing those within the IETF? We also have another kind of category that we've been seeing work proposed in, which is basically, can we update existing specifications to reflect reality? There's a number of places where we've published things either recently or very not recently that differ from what people are actually doing. And so we've got a number of different places where we're talking about, hey, can we update this to make things make sense? And then as we go forwards from there, there's a whole nother bucket of congestion related topics like delay and queuing and pacing and multipath and all kinds of cool stuff there that we can open the doors to depending on where there is interest and actual, again, intent to deploy. So with that, we filled in kind of some of the things that we've talked about either in this session just now, so that should be very fresh in your memory, or perhaps you need to go page in some stuff from previous IETFs. But we've talked about BBR, some variant of V3 and how we want to handle versioning there. Prague, we just looked at HPCC++ and Scream V2. And then we've also had some conversations just now. We talked about rate limited senders. And then previously we talked a bit about Reno and potentially updating things to reflect the reality of what's going on there. So we did some polls already this session. The goal in the next 2 minutes is not to suddenly say yes, and this particular one on this list is my absolute favorite, and let's do it. The real place that we're looking for feedback is what are we interested in working on? Does this make sense? Even if you don't have time to give feedback right now, grab one of us in the hallway. We'd love to talk about where that's going and how this is working for you. The real goal here is to make it possible to do this kind of work in the IETF in a fairly low friction manner. So I see we have Martin Duke in the queue. This is the end of
I didn't realize that text was a lie. Yeah, I mean, I'm curious what the chairs are thinking of as a timeline. I mean, I would be very disappointed if 5033 bis isn't gone well before Vancouver. So do you want like a draft charter before Vancouver via the list, or are we going to have another kind of menu kind of like we had today in Vancouver, or what?
Plot twist. I said this was the last slide, but we've actually got another one. You have a very topical comment. So yeah, so we've actually already started talking about and working on what would updates the charter look like. We're actually chartered right now, and we'll obviously talk about this in more depth, to talk about pretty much everything that's on this list. The main updates to the charter are going to be reflecting the fact that the BIS is actually out the door and going. So timeline-wise, yes, I think exactly what you said. We're trying to move that along before Vancouver and have everything in good shape to move from there.
Alessandro Ghedini, Cloudflare. So sort of remaking a point I made earlier about, one thing is defining the congestion control, another is implementing it correctly. I wonder if there's any room for, work related to testing, implementations of congestion controls, things to look for, what sort of scenarios people should test.
So we have 50.3 bis obviously as a starting point, but we just now in ICCRG, if you missed it, we talked about testing congestion control, and I brought up the idea of a hackathon in Vancouver.
But yeah, just quick thumbs up, thumbs down around the room. Is that a thing that you'd be interested in seeing here as well? I mean, we'll coordinate where that goes. I see a couple of thumbs up going on. Yeah, I think a big part of this is we're talking about empirical evidence of safety. And one of the challenges that we've had in the past is that whenever, say, I were a proponent of a new congestion control algorithm, if I showed up and said, hey, here's my evidence that this is safe, the response is, great, here's 3 more things to go try. And you can repeat that essentially infinitely. So if we were all pretty on the same page with what kind of tests and how we want to do that, that would be a beautiful thing to also make easier for people. And automate, yes, please. Beautiful. All right. We have drained the queue with that. Please do grab us in the hallway and give us more informal feedback as well. We're here to make this pleasant and happy for everyone. Wonderful. All right. Thank you so much. That is the end of Congestion Control Working Group at IETF 119.
Thanks, everyone.
Also, thank you for taking notes.
Yeah.
Very appreciated.
Good job. I'm very happy now.
Places to put docs. I think we should just charter congestion control dispatch.
Yeah, I saw that. Thank you. This was an
we've done an
session.
informal.
Didn't get everything talked
Yeah,
about.
that's what I want to say. I got the few question marks and
I filled a few.
yeah, okay.